Alright, so let's start with today's presentation. It will be again moving back into more theory, and then maybe to the next class we will again delve into some coding. So for today, the class will be, or I will start with repeating some of the concepts from last class, and at the end we talked about some things that I think I didn't have much time, or I didn't have like as nice explanatory examples in the slides as I could have, so I did replace some of them and added some real world examples, so it might be more easy to understand with that. And then we will move into generative models, which is a big category kind of, and then at the end a little bit about other types of data, how they can be encoded, but possibly that category might be again moved for like the next class, because just it might be interesting to have some hands-on with like representing data, maybe next class I'm thinking, but yeah, we will see. I will see what I'm able to prepare. Okay, so there are 2 points last class which were a little bit, I don't know, maybe I didn't explain them that well. One of them was searching about the distance between images and then between features and what is the difference, and that there is some difference. Maybe it's theoretically simple, but I have some more images here, and then also what is the difference between training a whole neural network from scratch versus using it like last time, like reusing some weights. So the naive solution with searching with images would be comparing them just like pixel by pixel, so something like this. And maybe a question to you is, why would this not be such a good solution, or such a good idea if we are comparing just pixel value by pixel value?
Like you would hold like the neighborhood that como todos los píxeles cercanos no se relacionan tan bien, o sea, comparar un píxel con otro.
Yeah. Yeah, and also like if we just flip the image, it should be theoretically the same image, but all the pixels are in different places. So like just the fact that like the cat has a head here, whereas here has the head here, like this would give us a big difference, because there is a lot of information here and there is basically none, and like it would think that these are 2 different cats basically, which they are, but we would like them to be recognized as similar, because I think this is some kind of Siamese cat and it should be relatively similar. So what we do instead is we did the VGG16 like last time, we encoded them in features, and then if we compare with inside this feature space, inside these 4,000 numbers, what we are comparing instead then is kind of like high-level concepts. So if you remember this illustrative image, we are kind of comparing how much is this neuron or this part of the image firing versus in this image versus in this image. So in theory, this should kind of pick up, okay, this is the face, and like one of them should be somewhere located near the face, and in the second image the same. So it is actually comparing the same parts of the image or same concepts of the image. So that is the biggest like idea behind this. So okay, this was like an example with cats. Again, that's not the only thing that is happening. There is a project called OpenFace, which has some papers behind it, but this is just as a like easy example. They work with like finding in an image, finding inside the image some where the face is. Wow, I'm fighting with my mouse now. Okay. Okay, we'll make it easier. They are trying to locate where the face is. That is using some basically non-deep neural network methods. And then when they isolate just the face, they use deep neural network model to get some feature representation. So when this disappears, they have 128 units or feature as a kind of as a representation for this face. And if you have this, and if you have a data set of other faces also represented in this 128 numbers, you can have like a kind of comparison with each one of them and see which one is the closest. And then you say, oh, this is the face probably. This is the person that we are looking for. Or maybe it's nowhere in the data set and we say, okay, it's someone else. So basically it is using the same idea as this simplistic example, however in a specialized network trained on faces. So that's what is different here. Just this basically, this neural network, because they have it trained on their own set of many faces. Okay, so kind of the second part for last time. What is the difference between training a whole neural network from scratch versus using some parts of it and then like using some classifier that we created last time, versus even one more method that can be used. And while this first part, training everything from scratch, is really hard and basically, I don't know, in some cases it's not even feasible when we don't have data. Something like this is workable and kind of can even be state of the art in lots of areas that we have just thousands of images instead of millions, and still we would like to do some classification in them. This kind of works. So how these three are different. So the first one, I think this is VGG network again, VGG16, and we just loaded the network without any weights. We just loaded okay, this is a convolution, there will be downsampling, convolution, downsampling, etc. Just the architecture with no weights. And then we have to train all of it. It requires a lot of images because inside here there is a lot of parameters to be set. Versus last time what we did was we just loaded the almost whole VGG network, cut off the end of it, and then added small classifier that had maybe just one layer, and then train only this. So instead of training this whole thing, we don't do it. We actually fix it, like freeze it. We feed images here at the top and get some features here. That's like a pre-processing part, and then we train only on the features to labels here. So whereas here we were training the whole network, this took a lot of time and also needed a lot of data. This actually didn't. This is relatively fast because we are training just this small model. And okay, so yeah, the problem here becomes that this network maybe is kind of like very usable for ImageNet images, but not many other things. So if you try to feed it some biomedical photographs of cells, and you would like to say, okay, this is a killer cell and this is a safe, like, I don't know, healthy cell versus cancer cell, maybe it doesn't, in this hierarchy, there is not enough information there because it has been trained on ImageNet datasets. It's been trained to recognize buses, cats, dogs, these categories, and not really this. So sometimes it can also be like, okay, if we combine it enough, maybe it can actually recognize some of the good image versus bad image, but it's hard. So what is done instead is, again, using the same thing, but the difference between these two, while loading this, we unlock this while training. So we still use these weights, but with a really small learning rate, we allow them to change a little bit. So this whole network then adapts to our problem, kind of. It's not locked to just training these, because maybe here there are the 4,000 numbers, so training from 4,000 to some other categories maybe is quite hard. Here we actually are training from some in the middle features. So, I should have brought the image here. Instead of training just from these, we are maybe taking these intermediate level features. So this is this allows us to work in areas where the data set is like maybe really different than ImageNet. Yeah. So there is the comparison. Training parameters for the first one, it is like more than 100 millions of parameters. That takes a lot of training, and basically that's not feasible for almost any problem here if we don't have this big data set. The second one, on the other hand, has 6 million, which means basically we are training just one net. And if you remember, there was a lot of connections between the convolutional output and the fully connected layer. So okay, it's 6 million. It sounds like a lot, but if you compare it with 138 millions, it's less. And the third one, basically, while also training the same one classifier, one dense layer here, we also unlock maybe 3 convolution layers, maybe these 3, and okay, in that case it's 13 million. So roughly, the more parameters you have, the more data you need. So you can compare the first one, it needs a lot of data, millions of images, we don't have that. The second needs quite little images, whereas the third one needs still like a little bit more. But there is possibility for the third one to be adapting to our problem better. So what you try is you try this method and see it works. Okay, it works, and then you try this method and you can probably get more like higher accuracy with it, because the model will fine tune towards your area that you are training it on. So again, to bring it from cats and dogs into some real world example, there is a researcher here at UFRO, Milara Kurilam. She's a researcher here at one of the departments, I don't remember exactly which one, but she's working with seismic signal of volcanoes analysis, and basically trying to come with a solution how to classify signals like this into labels like this. So while it is a bit different problem, because the seismic signals are a little bit like audio maybe, so they are a little bit different, but you can represent them as spectrograms, as these images, and this is actually what maybe the scientists who are exploring these signals are also using. They will visualize it like this, but you can use these images as your training set, as the images, and then these labels as the classes. So instead of having 4 types of cats, maybe now you have 4 types of signals. And just visually here you can see, okay, this like they look different at least. That's a good start. If they at least look different, there is some chance that the model will be able to like train and recognize in between them. So while this would be impossible to train the whole network in, well, actually, it would be possible, but it would have to be a really small network and with really small images, and maybe it would not achieve the high accuracy. So that it is possible to train a new network as well, but there are some limitations to it. But you can also reuse the VGG network and either fine-tune or either have a new classifier at the end, or actually fine-tune a bigger part of it. So yeah, basically this is what you can do then. You have images and you have some labels at the end, and this is a model that is the same VGG that we used last time, just with some fine-tuning. And I think this kind of approach is something which can actually reach a lot of like almost state-of-the-art in a lot of the areas. So there is a tendency of like each study field, each area of research to be staying in their own kind of like, hey, for 20 years we did it this way, so we will just do it this way. Maybe we will add some more parameters somewhere, like to make it better. But it is possible for like these areas. Actually, machine learning can be used in a lot of other areas, and it can boost a lot of their like accuracy of the classification problems. And yeah.
Está diciendo que lo que está haciendo acá, la base, entendido que están básicamente tomando la misma red BGG que fue usada la clase pasada para otro ejemplo, en este caso del volcán, ¿cierto? Casos con imágenes sísmicas, de frecuencia, etc. Y justamente, como esto está creado, se puede ver que se puede usar como state of the art, como estado del arte, como prueba inicial en muchas otras áreas. O sea que muchas veces otras áreas tienen como súper un modelo de hacerlo y no ocupan otras cosas porque saben cómo encerrar la suya. Pero con machine learning, sobre todo con redes neuronales que estén como creadas, se puede como tomas todo nueva clase de imágenes probando desde ahí.
O sea, tú tomas el entrenamiento que ya tienes, por ejemplo, con mis máquinas, y después tú le seteas los layers y las nuevas imágenes.
Exacto.
Y después tú, en el fondo, vuelves a entrenar eso.
Sí,
To here? Right.
sí, o sea, en vez de crearla desde cero, se crearía de scratch como las últimas nomás. Como lo que hicimos en la clase pasada y con el perro y el gato. Y como se requiere harta menos data, harta menos imágenes, más
Igual
fácil.
súper útil agilizar el trabajo.
Qué loco, igual.
Sí.
Como se extraña.
Wow, great, kind of crazy.
Yeah. But I think why it works is because in here, these low-level features are kind of generic. This I think would work for any image, kind of. They will work for some images, while these are kind of special. Like now these are trained to be working with elephants. But so if you use this for plants or signals from volcanoes, maybe this will not work. But something like here, maybe these shapes are similar in a lot of images, so maybe you can reuse it. And if you allow it to train up to here, it will kind of start on the with whatever it learned from ImageNet, and then it will like tweak it. So keep the stuff that is actually useful and change the stuff that is not useful. And it will be it will train on another data. So for example, this is one possible approach or one example when it's working with kind of vastly different data set. I have been working with images from Google Street View, so just like images from Street View. That is like it's very free. It's very easily obtainable data set because you can just download it, and then you can train with this as well. And I use the same basically method. I also like I adjusted the weights from VGG network, and it worked in some classification. So it's kind of powerful. If this is the only takeaway, like this could be for a lot of problems. If you try this, you can I think get good results, which is right. So I was predicting that there might be some questions. So yeah, I like we talked about it a bit. Are there some more questions maybe about the?
¿Cómo funcionaría? Porque ImageNet es para reconocimiento de imágenes, ¿cierto?
Sí.
Reconocimiento de sonido, por ejemplo, ¿qué se podría ocupar ImageNet o ya ahí estamos hablando de otras cosas?
Pues de sonido es, well, I mean, it's a signal of sound. You can convert it or visualize it as a spectrogram, which then becomes an image.
Yeah.
So, and then you can use the same methods, but it's a bit tricky because in this you have time, like each slice is a time, and in this you have frequency. So for example, like this one thing got dissected into these things. So like the x dimension and epsilon dimension is something different. So it's a bit tricky. So it might not work that well, but it is still working a little bit.
O sea, como que las transforma imágenes como para poder comparar audios o cosas
Ajá,
así.
más o menos, pero tampoco son tan exactos.
Claro, me imagino cómo representas tan bien un audio en una imagen.
Yeah. So at the end I have like few slides about representation of audio as well, and maybe the next class I will return to it more as well because I don't have enough for sure. But yeah. Okay. So.
Otra,
Yeah.
como en cuanto a tiempo de entrenamiento, por ejemplo, ¿cuánto se demora aproximadamente entrenar a la vez? Es decir, como comparación entre los tres métodos, tiempo.
Yeah, okay, that's a good question. So the first one, it takes a lot.
How much
This is really changing every day or every year maybe because new graphics cards are being made and etc. So maybe the first, the AlexNet model that we were talking long time ago about, it was actually trained on 2 GPUs because it didn't fit on 1 GPU. And so they even cut up the whole network, the images like 1 and 2, like the whole network, they had to change the architecture for it to be fit on 2 GPUs. And that took days, I think. I think in this case, it would still take some days. This could take minutes, actually, and this could take hours. Just as a comparison.
Yeah.
Maybe not that many hours, and maybe not that many It's actually it's getting quite good now these days. But it also depends on how big is your data set. If you have millions of images or millions of data, you have to feed everything there and then back and then back, and that takes more time. But it's true that this is also the difference between these models.
Yeah.
Okay, so we are going to the next category, the next biggest area of this class. I don't have much pauses inside of it, so I'm thinking either we can have a short pause here, or we can just go with it through, depending on you. Okay. Okay. So and you can pause me if you don't get some idea. I think I also added some like question slides in there, but just so you know, yeah. So what is the task of generative models? So it is if you have a data set of some images or data set of something, we can work with images because it's easily visualizable. So data set of something, and you want to generate something new, which is very close to whatever already existed, but different. So they are similar, but not the same. So this task can be extended to images, to text, to audio. So for example, with text, you can generate realistically looking articles or poetry or song lyrics. With audio, you can generate actually like some chiptune music that sometimes that's not that like it doesn't sound that difficult. There is not much variation. You can generate these things as well. With images, you can generate faces, as we've seen, generic images of rooms, basically anything to a degree as well. And the uses of these methods are kind of okay. That's probably for the first class that we were having. Some of the examples they were using these methods. Or these tasks they were applying it for something. So there are various methods. A lot of methods probably. We will start with the easiest one, which maybe there is some easy intuitive understanding with variational auto-encoders, and then we will move into GANs, generative adversarial networks, and yeah. So starting with auto-encoders, we have. This is what we already did. We did have image. We have some neural network, and then we are able to squish it into a feature vector. Basically, we have some numbers here that it was maybe 4,000 last time or something like this, and then we can train a classifier here which will tell it it's a cat. So this is the easy task or something that we already understand. And if we forget this part, if we just keep it like this, we have a structure that can encode a high dimensional image into some low dimensional vector from 200 by 200 by 3 image, long vector if you flatten it, into something like 4,000 numbers. Fine, nice, that works. What if I told you? No, these are the tools. Yeah. What if I told you that we can add something here that will actually continue with this? So these were the two main methods that were used in this starting encoder network. Basically, we were able to convolve, meaning we looked at an area and take some sample of it, and jumped with the same area over the image and reusing the weights, and then pooplooling, which is basically downscaling it twice or maybe more times depending on what you want. So making an average of this and getting us as a pixel. There are other two inverse operation to these, which can do the same but other way around. So upscaling basically, from one pixel getting more, okay, and deconvolution, which is going from this one pixel into a bigger area. So while the first was from a big image representing it into smaller, the second, these inverse operations are kind of moving the other way around. So from something small, they're increasing the dimension of it. So looking at convolution versus deconvolution, in convolution, we had the original image, we were jumping around it and with an area. Deconvolution is basically the same. Inputs of the image are blue at the bottom, and this is what the outputs are. So while convolution was taking from maybe 4x4 into 2x2, this can do the same thing but other way around. So actually increase the size of the image. And while it looks like an inverse operation, it is the same. It is written as the same calculation. We are again jumping with some area. Maybe here we have zeros. We kind of pad the original image with zeros, and then we can do some operation like this. So for the coding, it's the same thing. So in the network, the same thing happens. Only it is kind of.
¿En qué caso ocuparíamos la deconvolution?
So why do we use it?
Sí.
So this is this slide. If we want to add something here, which will be taking from the 4000 vector and reconstructing it into the original image, into the big 200 by 200 by 3 image. So this is where we use a decoder network or deconvolutional network. So while here there were convolutions and downsampling, here we have deconvolution and upscaling. Basically, two inverse operations.
Un ejemplo real de uso, o sea.
A real world example, like
Claro.
when do we use this?
¿Por qué tú harías eso?
Yeah, but why do we even build this as a model? So I don't know a real world example exactly for using the convolutional, but in this model we use it. So I will explain what is this model. So this is something which can take the original image, 200 by 200, smoosh it into a small one vector representation of 4,000 numbers, and then again reconstruct the original image. And this is just the model architecture. So in this, if we have this, we can then say, okay, we would like to look at how well is the model doing, how well, what is the difference between the original input image and the output image. And we can see, okay, we can train it so it's doing it nicely. So we can train it so it's doing basically nothing. From any input, it will just give it again. Why do we want this? Well, if we, there is a, okay, I will jump few slides in front. So basically, and then return. What we can do is we can take some image, smoosh it into a really low level representation. In this case, it's just 10 numbers, and then again reconstruct it. Here, it will not be the same. There will be some maybe noise, but it will be the same image, roughly. So the idea is, if you, from the whole network, if you just take the second part, you can, basically looking at this part, you can change these numbers and generate new images. Because we call this starting part a encoder, or convolution, or let's go with encoder. There is a lot of terminology with it here, which maybe is just redundant. It's not necessarily anything new. So encoder can encode the original image into this, and decoder or generator can go from these numbers into the into a reconstructed image. So if we toss away this part and we just work with this, we have a generator. So we can change these numbers and generate new images. That is the whole idea. So I will go a little bit back. So this was the rough sketch of the model. Here we have it more kind of in more detail. So this is again the VGG network. We have the starting network. It will just compress it into some small vector, and the deconvolutional network, the decoder or generator, will be working in the other way around. So you can train it to basically to force the model to be generating the same image. As I was saying, the naming scheme is a bit difficult. So like they are using a lot of names for the same thing. They call it convolution network or encoder. This is a feature vector or also latent vector, and this is deconvolutional network or also decoder or also generator. Basically, those are the same terms. I will be trying to stick to generator, referring to this, encoder, controlling this, and feature vector or latent vector here, but it means the same thing. Also, we have some this is the same thing. We can call it input, some code, and some output. Okay, so are there some questions now? Okay, so everyone gets that from some big image, big dimensional representation, we can smush it into maybe just 10 numbers, and then again reconstruct it into a bigger, the original image. That is kind of.
Queda bien parecido.
It looks kind of the same.
Yeah. So the magic of this, like here, if you look at the individual layers, we kind of maybe know them. These are the convolutions. Again, convolution. This is twice smaller. Some convolution, some convolution. This is again smaller, so you can see a lot of pixelated images here because these are just downscaled from this. And there are fully connected, so this is just a lot of numbers. This is just a layer of all neurons connected with everything. And again, the same thing here. And this was the encoding part, which then smooshes it into just 10 numbers. And then at the reconstruction side or the generator side, we have the same thing basically on the other way around. So we reconstruct from these 10 numbers some larger vector. Again, these are just dense layers, fully connected layers. And then we use the convolution and upsampling and deconvolution and downsampling, I think. And again, I think this is, I don't know what happened here, but I think it's again the deconvolutional into just one. So this combining all of these into one image, and then here. So now we have trained it, and now we can now we have a model which can, from whatever we give it, it will give it back. We spend a lot of work on training it, on doing nothing basically. It just returns what we gave it. Except in the middle, it was able to smoosh it into really small dimensional space, into this vector. And here is where we can work with it actually. We can change this and then kind of change what it generates. So we totally throw away the encoder and just work with the deconvolutional or with the generator. So let's say we have a number 2 and we know what the vector was what the vector that represented it was. So maybe this is the, let's say, 10 number representation of number 2. And if we give this, the 2 to this network, it will generate 2 image. If we also know what is the latent vector or the feature vector for 3, and we can feed this generator with it and generate 3, fine. But what we can do, we can create new, kind of give it a new vector and generate something totally different, what we did not train it on. So for example, somewhere in between the 2 and 3, we can feed it these, like a vector which is just combination of these two vectors, just in the middle of them, and it will generate us something in the middle of 2 and 3. So this is like an image which is somewhere in the middle of these two numbers. Or here it's more like 2, here it's more like 3, because we were like feeding it a bit of that or a bit of that. Okay? So we have latent vector, which in this case is just 10 numbers, but in general it can be like 500, 4,000, depending on whatever the model architecture was. And the values of this vector can move around from 0 to 1, and basically there is a lot of possibilities. This space where this one vector can move, all the possible values for it, is called latent space. Just means basically we have 10 numbers and all of them are coming from 0 to 1. So the all possibilities that can be fit into this one vector are called latent space. So the latent vector is moving around the latent space. It is just like as a terminology then to talk about it better. Okay? So good. However, the thing is that a lot of these vectors will actually generate just some noise. So if we give it some random numbers, it will usually generate some nonsense. But what we can do is we can like feed it a vector for 5, we feed it a vector for, I think this is 9, and then generate something in the middle. And because, okay, this is relatively boring because we are just like sampling something in the middle of two numbers, we can also do it with a data set of faces. For example, this is a big model that trained our faces, and then we gave it vector representing this face and vector representing this face, and then we can have an interpolation between the two faces. So, okay, it's quite like, this is something different again than working with pixels, because if you interpolate just pixels of this image and pixels of this image, it will look ugly and messy, and probably maybe some on one the face is like this, on the second the face is like this, so you will get like two faces in the middle because you just took half and half of two images. That doesn't work. But in this case, it actually can like, okay, it can sample from yeah, okay, it's actually like, this could be like, okay, a middle of these two faces. Yeah. So this is not limited just to images. It is whatever you can represent and train a model on, you can interpolate then in. So this is like interpolation. We had a model which is able to represent 3D objects, and it's called voxels in this case, which is, we have a grid of 64 by 64 by 64. We have a cube, and if there is 1, it means that there is a solid point in there. If there is 0, there is nothing. So it's just like Minecraft, for example, there is a lot of boxes, 64 by 64 by 64 boxes, and you can represent a chair like a matrix of 64 by 64 by 64, like a box of numbers. And then there are some tricks how to change this in the encoder side from this side into going back to vector, and then on the decoder side again from vector back to the original thing. And then if you have the decoder or the generator, you can just interpolate between, okay, sitting chair with some, I don't know, an armchair into a tall chair. Yep. Some questions? Doubts?
Sí.
Yeah, we are getting into an area which is not so, like, these are kind of not traditional machine learning models. So it is also sometimes hard to imagine what this could be used for. So with the classification, you can say, okay, I don't know, in a cars, this is a human, I should slow down. But in this case, like, what the hell is this used for? So, so this is maybe where, like, to some degree, it's touching a little bit of art. So maybe you can say, okay, I want to generate new chairs, and you will sample from like somewhere in the middle of what you already created, and you can like make new things. Or maybe you can generate new faces and then try to fool someone with the new faces. So there are like, it's not traditional machine learning. This is kind of moving into.
Para hacer esto solo necesita 2 imágenes y las interpola, nada más.
O sea, y entrar un poco todo el sistema. O sea,
you need the big data set of faces to train the original network. So basically, to train this, you have to have a lot of data. And what kind of happens is that this network learns all the faces inside of it, and then if you give it something new, it will generate from what it already knows. So, like, this face is probably, it is just taking from these two, but also from other samples from the dataset. It couldn't do it on just 2 images. It had to have a bigger dataset behind. Yeah. Okay. So, and this is even more wild. So we can talk about this feature space, this latent space here, and we can like, okay, we can imagine it. This is a space somewhere. There are 10 dimensions in this space. We know that this is an area where there are all the ones, and this is the area where there are all the lines or something. And if we work with faces, we can also say this is the area where there are all the woman faces, and this is the area where are all the men faces. But can we like look at this, have some average here, and then kind of try to move it there, maybe. And actually, yes, which is a bit crazy. So there is something called arithmetics in this latent space. So you can take a image of smiling woman, okay, that corresponds to some area of this like strange dimensional space that we cannot imagine, but we can roughly visualize it as a ball. Okay, there are these faces that are smiling and they're women. Fine. We can find another cluster of like neutral woman faces. Fine. And by the way, these are some horrible like generated examples. So just like there are better models which can do it better. But this was the first paper which kind of did it, so that's why we use it. So from this cluster of like smiling women, we can get a representative feature here, and like minus a representative feature from a neutral woman area, and then we can add it with a feature from the neutral man space, and what we get is something like a smiling man, which is a bit crazy because we have transplanted a smile basically, and yeah, okay, this looks horrifying, but actually it like actually I think it's using this guy and giving it face and giving it smile. Okay. So the same thing you can move around with glasses. Again, some of the results are pretty horrible. Sometimes this looks strange, but you took men with glasses minus men without glasses. So I don't know what becomes like from these two. I think you have a feature which represents glasses somehow, and you can give it to the woman without glasses class, and then it will be moved here. So it's a bit mad. Yeah, I think I have a question slide. So basically we are moving around like some we have represented the data into some like 10 number space, into the latent space, and then we are moving around this latent space. So the fact that some area is like, okay, this is reserved for women, and this is reserved for men, and this is reserved for glasses, or men with glasses and women with glasses, it just means that they are visually distinct. So the model trains, and it really depends on how the model trains, but it will learn that, okay, they look different, so I will put them with different numbers into this like maybe 10 numbers I have. So that's why you can do the arithmetics with it later. Okay, some questions about variational autoencoders. we can have maybe actually we can have a small pause now, because I think the next part is scarier. Yes. We can have a small pause now.
La próxima parte es la idea mía. Ya.
Estaba preparando.
So,
¿Hace cuánto? Hold on. ¿Hace cuánto está esto? ¿Hace cuánto existe? How old is this?
Oh my god, I don't know actually. 2000. It will be past 2012. So after that, I would think 2014 or something. The first paper started with this. Or actually, variational autoencoder. This model is roughly. It's relatively simple. I think because I don't know actually. I can look it up. But it exists for a long time. The problem is that the faces look strange. They don't look realistic sometimes. That is the problem. First, I don't know how to call it. So there is something from 2013, but I don't know if it's the first one as well. Maybe not. Yeah. But machine learning itself also is pretty old field. So the model of like from the first model, the LANET, it was like 89 or something. Someone came up with it, and before it there was a multi-layer perceptron, which is basically the same thing.
I was
That
like
existed for a long time.
comparing and taking like mashing stuff together,
Yeah.
making mimics is like
Yeah.
La imagen del tipo riéndose se parece al cuadro que la señora repintó para arreglarlo.
el que sube del
Ah,
¿cómo se llama? Ex-home?
no, pero ¿cómo se llama?
But I think the kind of trick is that in this sphere, like it sounds strange that you are generating new women with glasses, but in this sphere maybe you had to have examples of all these things. So you had to have like men with glasses, then just men, then just women, and just women without glasses. And then if you are moving around this, you have to have in every one of these categories a lot of examples. So it kind of can say, okay, what is the average image from here, plus what is the average image from here, minus what is the average from here, and to kind of get here. But it's a bit tricky. I'll go for it.
Se parece un poco.
Me recordó eso, definitivamente.
No sé, se parece. Parece. Infinita, sí, hecho atrás. Sección infinita.
Okay.
Se parece a eso.
Uh-huh.
Al
It's not the same. But there is someone who represented these images, like religious images, into a latent space, and then you can move around with them, and you can see how they are changing.
this metric,
Is
las raw, a woman for restoring this.
Ah, right. Oh no.
Now is meme.
Ah, okay. I didn't know the origin of it then.
Yes.
Okay. Yeah. So these methods could be better maybe. Okay. So right. Are there some questions about the variational autoencoders, or about the latent vectors, or about the latent space?
Mostly, no, I think the mathematics for latent space are kind of complicated, aren't they?
Maybe not much, because it's just you're filling like a vector with numbers, but what happens then is complicated. What the model recreates is maybe complicated, because the generator can only like create what was in the original data set, but it can make some like middles of there, so like some interpolation between them. So yeah. Okay. So let's move to the next one, which is called Generative Adversarial Network, and it is the task is the same, to generate new images that look similar, or new something, let's say images in this case, can be different data as well, that looks similar to whatever we had before. And so the goal is the same, but the path or the model that is being used is a bit different. So in this case, they used a sample of two models. One is generator, which can generate new images, and then there is a discriminator model, which can say, okay, this is generated, whereas this is from original dataset. And they have two models, and they are kind of combating against each other, trying to learn a task. So if you put it like this, there is some latent vector, we had this before as well, some feature, and we are generating an image. So this generator will have a lot of deconvolutions, upsampling, basically the same thing that we saw last time, okay? Then also we have a dataset of real images. There is a lot of real images. And then there is another model which we feed with all the real images and also all the generated images, and we want to teach this discriminator. Basically, discriminator is again going. It is probably classifier. It is classifier. It is something like VGG. It is just going from the image to two classes. One is real and one is fake. So we train the first one to be better at generating images, and then we train the second one to be better at recognizing those generated images and those real images. And then of course, because like we started here and there was nothing here, we don't really know what, like, we started with training the generator without kind of being able to compare it with the real images. So we have to train the generator a little bit, train the discriminator a little bit, and then come back to the generator and again train it a little bit more, and then come back to this one and train it a little bit more. So it's kind of iterative process where you always try to make the generator a little bit better and then make the discriminator a little bit better. And then you come back to this one and then back to this one. So the process is really difficult actually. For training, for example, what if the generator is too good and it will just generate images that are too realistic? It will like kind of run away from the discriminator, and you have to kind of balance these two. You have to balance the amount you are training this one and this one. And also it takes a lot of time because you are training this one, 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 this one. It's slowly moving somewhere. So the where it is actually moving slowly is towards generating nicer images. So this is the same scheme that we had last time. So we have some vector, we generate images. These are fake images, and then we have a dataset of real images, and we train the discriminator on real or fake. And then we somehow propagate the error here and get like to fix the weights in all of these, to change them, to train it. So the first, sadly, like we cannot really, I mean, we can visualize the generator's outputs, and we can also say how many the discriminator was able to assess as correct or not correct. And this is basically the visualization of the generator. So first it starts with some random noise, because we had nothing in it. This was just, there's nothing, there's some zeros in the model. So it will generate some nonsense. But slowly and slowly it will actually be able to generate more and more realistic images. Yeah, I think I have some videos on this training. So let's start with faces, I think. So from the first ones where they were not really that good, okay, I can make it maybe bigger. So again, if we go to the entire start, there is nothing in there. There is just noise. And then it slowly moves into something like faces. Yeah, okay. HD. Yeah, and it ends with something looking quite okay. Some of them are maybe not that, yeah. Okay, it's detecting the end of the, yeah. Maybe some of them are actually wrong. Like if you remember from the first class, we were also showing some of the images. Like some, like maybe sometimes the eyes are not correct and stuff like this. Sometimes it's a bit blurry. This is a nonsense, for example, yeah. So you can use the same thing to train on different types of images as well. So, for example, oh my god, I will not be able to. Okay. you can generate images of newspaper pages. So it starts with like a bit of nonsense. It still looks a bit like nonsense, and maybe I can make it look nicer. Maybe. Yeah.
No.
And okay, we can at least see like the in the middle process. It is actually okay. It is getting something. You cannot read it as like the letters. I can jump in front a little bit because it's a long video. But so you cannot read. Okay, there is this letter or something. But if you saw it from like really far away, like this, I would say, yeah, this is some newspaper. I don't know which, but yeah, some newspapers. And this is working just with images, actually. Again, it's not like you could generate newspapers by generating the text and then placing it yourself, but this is just generating newspapers as image. So this is some visualization of the training. Wait, can I make it big? Okay. Right. So if you remember, in the first slide, we also on the first lecture we showed example from this year, which was working with GANs, Generative Adversarial Networks, which were able to generate way more realistic images than ever before. And it is this one, progressively growing. And the only trick they have, basically they also have the same scheme of training the generator and having a discriminator. And then like using whatever is generated as the result. The trick they do is they scale the image slowly from 4x4 to 8x8 to something with the pixels going slowly to a higher resolution. So when they basically they just add some convolution and deconvolution layers. So here they add deconvolutions and here they add convolutions, and it will just make it bigger. So and they will feed always the generated ones and some dataset of reals. Generated ones and some dataset of reals, etc. So while training generator discriminator, at some moment they will also say, okay, that's enough. They will swap into the higher resolution version. They will copy the weights over and like slowly initialize these with something sensible as well. There is a lot of details in this paper which are not really that necessary to understand, but basically what they do, slowly one by one, they generate all the way up to like 1000 by 1000. So this is relatively high resolution. Yeah, so these higher resolution images, we saw this video, but I think we didn't see much the training process. So let's go at the 49. Let's pause it, let's check it. Yep. So this is the it's not just the noise, this is also the really low resolution image. So this is probably 8x8.
It says 8x8.
Yeah. So it had a step of 4x4 before. Maybe they will show it as well. 4x4, yeah, that's really fast. So this, while switching between the generator discriminator is also switching between the resolutions. So it's kind of like added, yeah. So this is how they are able to generate. Okay, some of the faces still look quite monstrous, but some of them are quite realistic. So I think this is quite a big advancement in the field of GANs. Yeah. I think, is there anything else? Maybe no. You can also interpolate between these. So what they did is, it's horrible sometimes, yeah. But you can just go in the latent space. Actually, the latent space is you can imagine it as a space, and you can have a point which is just moving around in it. And this is what you can get. Like, there was a, yeah, some of it is nonsense, some of it is faces with smiles, some of it are horrible, yeah. Some of it works, some of it doesn't really. Yeah.
Como que se ve que está como cambiando, como fue.
But maybe this face would be realistic roughly. Maybe this one, yeah. So a big thing that is kind of still being discussed about GANs, Generative Adversarial Networks, is how creative they really are. Because if you generate a face which is looking quite nice, quite realistic, maybe it is one that is really close to whatever you had in the dataset. Maybe you are cheating in a way. So actually we started this whole chapter with the topic of what do we even want. I should put it there again. Anyway, this is a dataset, and these are the generated images, and these three faces are the closest one to this face. These three faces are the closest one to this face. These three faces are the closest one to this face, etc. So they argue that whatever they generated is far away enough from whatever the dataset already had, which is true to some sense, but you can still see, okay, this guy and this guy, he's a bit similar. This is a bit different, but maybe this guy and this guy, you can actually, maybe he's that with a different haircut. So it is, I think it is still open area of research how creative these really are. Like, and it's kind of hard. How do you measure creativity in this sense as well? You can measure some like distance from the training samples probably, but and that's what they use in these in the plots. There is some. If I go back, there is some Wasserstein distance or estimate. There is something going down, so there is some like measurement that we can make, but it's not really creativity. So that's the hard part. Okay. Yep. Some questions now? Maybe about this model, this scheme.
Uno comienza con el generador destinado.
Sí.
Así como sin ningún peso, sin ningún nada real.
Both of them are without anything, yeah. So that is why at the start the generator is just giving noise, and at the start also the discriminator is really shit at it. So it cannot even distinguish the noise from the real images. It has to train it. And then you go again, and then this will you propagate all the errors, and you basically you fix the discriminator, and you force the generator to be changing, and the weights. Basically trying to generate something that at that moment will fool the discriminator. And when that succeeds, roughly, you can say, okay, this is good enough, and then you again train the discriminator. And at start it's fooled by the generator, fine. Like maybe the noise is slightly nicer noise, so it is fooled again. So it has to train this one while this is fixed. So this is why one of them is always being trained and the other one is being fixed. Or I was trying to figure out how to make it into an animation here. I didn't. I did have these slides, but it's not the same. Yeah. Okay, so if you remember, with the variational autoencoders, we were able to move around in this latent space. In here, we also have a latent space. We also had a latent vector, which we feed to generative, which we generate images with. So we can move around with this vector Z, with this latent vector, and for example, add to an input a blonde hair feature or a gender change. This is maybe the biggest I can go, but or make them pale skinned, or make them angry, or make them happy, or make them fearful. And sometimes it looks actually strange, but sometimes it looks quite realistic. The gender changing is quite funny, I think, because like it will add some maybe beard in some cases, or maybe actually it will smooth out the faces so they look like nicer. So this is, I don't know his name, but he's a actor from like Dr. House. Okay, I don't know, but to see him as a female is quite funny to me at least. So. Yeah. And here again, now this is like a gender change, so it's cool, I would say. And yeah, so about GANs, there are many versions of GANs, and some are better at these things and some are worse. So while some are really bad at like, okay, if you see fearful, you transplant fearful for this face, some of them fail really horribly, but some of them are quite good. This is a like star GAN. They use various tricks to kind of to manage the space of the latent vector in a way that then it's easy to move around in it. So those are the tricks. I don't know exactly which they are, but kind of like to maybe move away, force it to have the cluster of, okay, smiling faces, these faces, have them far away, So it's easily distinguishable. It's distinguishable in that space to move around then. So that will result in some of them then looking more realistic if you move around with it. This is actually looking quite good, right? Whereas these are quite horrible. Yeah. I like this one. Beautiful. Yeah. So, are there some questions about GAN or about the training or about the movement in the latent space?
How much can the percentage error
Mm-hmm.
of the discriminator or determinative if majority is real or fake?
So, I think the discriminator is always training only on the stuff that is just now being generated and what is real. So, I think usually it can say, like, if you train it well, then you can distinguish everything here is fake and everything here is real. But that is just a point where you will switch to the generator to become better. I think at some moment these two, like this switching method reaches some moment where maybe you are not moving anywhere else. Like you stopped with the training because they cannot train any new information. So they're stuck in this. So maybe they don't change at all in the iteration. So maybe that is a point where the discriminator cannot actually distinguish. So maybe the error goes up of it, and the generator maybe doesn't change at all over several iterations. So that's when you stop, when it reaches some kind of equilibrium between these two models. But it's quite interesting because, for example, if you are generating faces, you can then use some other method, some other model that has been trained on faces, like the FaceNet that we were working with, like, or showing it like long time ago. And then you can plug it in the system and say, and this model is actually it's very capable at recognizing faces. So then you can actually say, okay, this is fake. But I think no one ever did in current research that they would combine this kind of like a neural network which would be trained on a, let's say, expert set, maybe just faces, with this model which is general. You can train it on anything, faces or images of furniture or of animals, of anything. So maybe there is some possibility to like hooking up another discriminator and like slowly then changing from this one, which is not ideal, into something more specialized. Yeah, expert knowledge. But
¿No se ha hecho todavía?
pienso que no. But, yeah. Good. Okay, so if there are some, it will be. I have a small section about the other types of data, and it's not really exhaustive. I think I will move it to the next part again, and maybe in more details. But I can like just open it up today. But if there are no more questions about this area, good. So, okay, we will be talking about how to represent different types of data, and basically that just means taking it from the original, maybe 3D matrix or maybe a 2D image or maybe etc. into some way how to represent it as numbers. And the important thing to kind of like realize at the background of this, if you can represent anything into like numbers, a matrix, you can then use these methods. So you can have a generative network which will be generating these things, whatever you just represented. Or you can have a classifier which will be classifying in between them. Okay, so there is a lot of types of data, but let's talk about these areas. So audio or signal, audio is just a signal, right? It's just some waveform going up and down. Let's start with that. So you can sample it. You can select like a sampling rate of 100 samples per second. So if you have this nice line, you can every 100th of a second just ask, okay, what is the number, what is the number, what is the number, what is the number? And as a result of this, you will have these numbers, and it's a vector. So we will have like a 100 by number of seconds you had sized vector. That's one way. Or you can represent it as images, which is the visualization method that we were talking about last time, and you have image there. You have in this you will have to figure out some other models, maybe with 1D convolution, or maybe something called recurrent neural network, which we didn't talk about yet. Maybe next time, because it's again a big category. But with this, you can then hook it with some other image classification models. So this can work with signals. This can work with some like recorded. In this case, it's a volcanic activity, right? It's not music, but it can work with music as well, with voice recognition, with translation from like voice into text as well. Maybe language recognition, and yeah, lots of these. Yeah, so this is really just an overview. If you have text, it really depends what kind of text do you have. So in English alphabet, there is 26 letters, and there are some special signs, so maybe some brackets, some dots, some commas, stuff like this. So you can say that each, if you have a vocabulary of some size, you can say, okay, every letter A will be 1, 0, 0, 0, 0, 0. If you have B, it's 0, 1, 0, 0, 0, 0, etc. You can like smoosh the whole vocabulary into this vector. If you have words, instead, it's a bit trickier because then you will have to have abacus 0, 1, 1, 1, 1, 1. Oh no, 1, 0, 0, 0. I don't know what the next word in the whole vocabulary of every word will be, but second word, okay, that will be 0, 1, 0, 0, 0. And that's trickier. So, but then you end up with a lot of vectors, and basically there is a different type of model that is being used, recurrent neural networks, which probably I will keep it for next time. The trick is that they are working with the thing with time. So well, when we had image, it was you look at the whole image at the same moment. If you have a sentence, there is some sense in the sentence I'm saying right now. There is some sense where do I put the words? So if I started the sentence, I don't know. I'm trying to figure out the sentence which can be shuffled around.
Are you hello?
Yeah. How are you? Are you how? You are. You how are? Some of them don't make any sense, right? So in that case, you would like for the model to say, okay, hey, this is nonsense. But in the last one, it's okay. This makes sense. So there is the whole like time aspect of it, which we need a different model of neural networks for, basically. Okay, and then map data. It's huge. There are also different ways how to work with it. So maybe you can have just pictures of the globe. Fine, that's relatively easy. It's an RGB image. Maybe that's Google Street View images as well, or aerial satellite images. But you can have also imagery with 3D data. So instead of just capturing an image, you will capture a map of like, okay, there is this like a lot of information. Or if you work with Google Maps, actually, in one of the representations, you don't even have like images and pixels. You have a point, line, point, line, point, line. So there is a vector representation. And just to work with all of this, it's again a different task. Ideally, you can convert it to something you already know, and then use models that you already know. But yeah. So the task that they do is, for example, from an image, segment it. So recognize, okay, this is a building, this is a road, this is a car, maybe this is a, I don't know, other, or like a greenery. Or you can try to like in a dataset of satellite images, find every tree and then mark it in a map. So that's another type of task. Yeah. And lastly, this is what we were showing before, working with voxels. I just left this running in the background. So how do you represent 3D images? And then maybe if you can represent it, then you can train these autoencoders on it, or some classifiers on it. So you can have a classification of this shape represents a chair, or this shape represents a toilet, or something. If you look at yeah. So what did they do is they had instead of having an image here, you have a 3D space here. And instead of having 2D convolution, where we are looking at area of 3 by 3 pixels, we have 3D convolution, which is looking at 3 by 3 by 3 box. Yeah. Okay, so that's it. This was just a really fast run about the different types of data representations. I don't know if you would be interested in it for the next class. Now is the last moment when you can still say, I would be interested in this and this and this, and I can change the classes for it. I was thinking to make it more practical next time. So maybe creating a whole model and then training with it. But maybe also we can look into the different types of data representations, and maybe I can like provide some codes which will be load a audio and then represent it as numbers, and then we can have a really small model just trying some stuff with. I don't know. What would be some area that would be of interest to you?
Sí, sería como interesante algo un poco más práctico.
Mhm.
Como de probar cómo será el...
Sí,
Okay.
como de cero.
Sí.
Mhm.
Like from scratch.
Yeah. Okay. Okay.
It's possible or
Yeah. It should. I don't know if the model will be able to train, but at least the code is possible to write, and we can see the worst case scenario. We can connect to other computer and then train on it. Actually, I can connect to the one there with team